We have been talking and discussing about the importance of relevance and similarity between the prototype and the model in the laboratory and their relevance, how important these things are. So when it comes to kinematic similarity, when that is achieved at all locations, the speed in the model flow is proportional to that at the corresponding locations in the prototype flow. So it doesn't have to be the same speed because it cannot be done so. But it has to be proportional. It has to have relevance. So for example, in the two pictures that are shown here, in the prototype the field is large, the objects are large, the velocity is large. And in the model on which the experiments are being carried out, the velocity of the model denoted by the way, the P subscript P refers to the prototype problem and M refers to the model in the laboratory on which the work is being done. And the thing that is trying to show here is, or argued here is, that the direction of the velocity should be the same. It should be proportional. It need not be the same. And similarly, the length scales. You can see the height here and the height here on this side, the drag and the forces. They cannot be the same, but they need to be proportional in the same direction so that we can have similarity and the result in the experiments are useful for making real life or prototype product. In general flow field, complete similarity between a model and a prototype is achieved only when there is geometric, kinematic and dynamic similarity takes place. This we have mentioned, and so I don't need to deliberate more on that. There are several methods for working out this similarity, for achieving the three similarities that we just mentioned, and one of them is known as Buckingham method or Buckingham rule. And for that, we let uppercase of Greek alphabet pi. You know that the number pi, which is the ratio 22/7, is denoted by Greek alphabet pi. This is the small one. The capital pi is shown as this. And this is what we are mentioning here, the capital pi. We let the uppercase of the Greek letter pi denote a non-dimensional parameter. In general dimensional analysis problem, there is one pi that we call the dependent pi, and giving it the notation, let's say y1. And obviously there will be an independent pi, there will be a dependent pi. The parameter pi1 is in general a function of several other pi's, of course, because it will be depending upon many other independent variables. So they are the other pi's. So the dependent pi, pi1, denoted here, is equal to a function of several other variables denoted by pi2, pi3, pi, and so on. It can be as many as there. To ensure complete similarity, the model and prototype must be geometrically similar, and all independent groups must match between model and prototype. When we talk about the group, we are referring to those numbers that I mentioned, the Reynolds number, the Froude number, and whichever is relevant. So if pi2 of the model is equal to pi2 of the prototype and so on, then pi 1 of the model will be equal to pi 1 of the prototype. This is the rule that is required for similarity. And for example, if we are trying to make a prototype car and we want to see that as the car is moving, what do we want these days? Fuel efficiency, smooth movements, streamlined movement, minimum of drag, so that energy is used to the maximum, fuel is used to the maximum, and the wastages are minimum. The important thing here is, again as shown, the velocity, the viscosity, the density. So Reynolds number is important here. The inertial forces divided by the viscous forces, because it is the friction that causes heat generation, that causes drag, and so on. So, and this is of course the length scale, the scaling of the body of the object, whatever we are making, is important. So here is an example of geometric similarity for model car and as well as the prototype if we are working on that. The Reynolds number, as I said, mentioned, comes into play here, and that is equal to the ratio as shown here. So it's important. And you can see when Reynolds number is large, it is only showing that velocity is high and the viscous forces are very small and they will have negligible effect. But if viscosity is high, the velocity is small, it's a different ball game then. So pi 1 is equal to the function of pi 2, and pi 1 here is given by the Reynolds number and so on, which is shown here to you.